So this is the second part of equilibrium, where we are going to need to solve for things usually not at equilibrium. If you are at equilibrium, obviously you can just plug things in to the equilibrium expression and solve for it. But if they don't give you equilibrium concentrations, they give you initial concentrations, you're going to need to use something that we call the Rice table. Some teachers call it the ICE table, but the Rice is, the R is the write the balanced equation, the I is the initial concentrations, C is the change, usually in terms of X, and then E is what the expressions will be at equilibrium, and then you can plug it into your equilibrium expression. Okay, so the first example we're going to do reaction, stands for the reaction. Okay.
Hey, what about what we did like last week? I guess, isn't that, like, you can use this in not equilibrium, right? When it's not?
The Q?
Yeah.
Yes, but that's when you're comparing Q to K. These questions are going to be asking you what is the concentration, and so you'll have to use some calculations. So in this particular example, whenever you see at equilibrium, whoops, that's in white, that's not going to work. When you see at equilibrium, you can do the happy dance because you're not going to need to use a Rice table. Okay, so we have this equation, and it gives us the pressures, right? 2.71. It gives us what Kp is. So we're going to set up our equilibrium expression, which is going to be the NO2, partial pressure of NO2 squared over N2O4, partial pressure of that. Okay, so when we plug in what's been given to us, we know that Kp is 0.133 is going to be equal to the pressure of NO2 squared over 2.71. So now it's just a math problem, right? So we're going to say that the partial pressure of NO2 squared is going to be equal to, after I take 2.71 times 0.33 or 0.133, 0.36043, and then to get the partial pressure of NO2, I'm going to take the square root of that. Do I need to write it? I'm just going to, okay, square root of that, and we get our answer. Okay, but that's because it had the magic word of at equilibrium. Guess what? The next one's not. No, they cannot. Matter of fact, most likely they will not be on the AP exam. They're going to want you to try to set up a Rice table somewhere on that AP exam, probably. No, it's just wanting to know that you know how to do it. Okay? Any questions on that one? That's straightforward substituting our math, right? All right. So, the next example we have, and you're going to need to pay attention to your volumes, okay? Because when we're doing our change, your change has to be in moles, not molarity. So you may have to take it out of molarity, put it in moles, and put it back. So it's something you're going to have to pay attention to. So you can do just a small, tiny little happy dance when you see a 1 liter, because then your volumes aren't going to matter between moles and molarity. If it's not 1 liter, you're going to have to do some other calculations. So we're going to start with the R part of the Rice table. So we have PCl5 going back and forth to PCl3 plus Cl2. Most of the time when they give you an equation on an AP exam like this, it's going to already be balanced. But double check, make sure they're not trying to pull one over on you, but most of the time it's already balanced. So we're going to do I, C, and E. So initially from the problem, we have 0.298 of the PCl3, right? I think that's a mistake. I think it's a... Oh, I have it backwards. I did it exactly backwards in my problem. So 0.298 here, moles, and 8.7 times 10 to the negative 3 moles here, initially. And then initially we have 0 for our chlorine. Okay? So this reaction, the change is going to be, we're going to call the change X. Okay? Since everything is a 1-to-1 or 1 in front of the stoichiometry, it's just going to be 1x. Okay, if it was like a 2 or 3 in front of it, it'd be 2x or 3x. So for the reactant, it's going to be minus x because it's going to go down by that much. For the other ones, it's going to be plus x and plus x. Okay? So then we draw a little line at equilibrium. Okay? And then they were nice enough to give us what x is. Right? Right here. They don't always do that. That's at equilibrium. So we know that this has got to be 2 times 10 to the negative 3 moles. So basically, at equilibrium, x is this much. Because that's how much chlorine was there. Because we know it's going to change by forming x for chlorine, and they gave us what that concentration is. So that means that this should be what? I don't have that. I did it backwards. I did something wrong. So 0.298. Get off my quadratic equation. Plus 0.002. Right? So that's going to be 0.3 moles. And then over here, we're going to have 8.7 minus 2 is going to be 0.0067. What? Where am I getting these numbers? I'm plugging in x. This is x up here. Because it gave it to us in the problem. They don't always. Sometimes we have to solve for x, but they were nice enough in this one to give us x. So I subtracted x here and added x here. So these are my equilibrium concentrations. So it wants me to calculate the equilibrium constant. So now I plug it in for K. Okay? So now I'm going to say we have 0.3 times 2 times 10 to the negative 3. And then divided by 0.0067. So I should get 8.96 times 10 to the second, which would mean K is, no, it's a negative. It's negative. Sorry. Since K is less than 1, what do we favor? Favor the reactants. Okay? So did everybody understand what I did there? Because that's actually an easy one because they gave us X. Okay? And honestly, sometimes when you're given X, it actually throws people for a loop because they're so used to having to solve for X. Yeah. Okay? So are we good on that example? Okay. So let's do number 11 is pretty straightforward. Exercise 10. I want to jump and do exercise 11 together. Okay? So you have the answers to that one, and I'm not going to leave myself very much space here. So I'm going to put a blank page because y'all can read that. Okay? Otherwise, I will not have enough room. So our equation is going to be H2 plus F2 is going to yield 2HF. Okay? And these are all gases and or liquids. So so there's our R, I, C, E. So it tells us that we have 3 moles of each, right? So 3 moles, 3 moles, 3 moles. So after this reaction happens, it's going to be minus X plus 2X. Why plus 2X? Because of that 2 right there. So make sure you don't forget to do that. Yes? Oh, I forgot to do there. Yeah, it is, yeah. Sorry. Habit to just do an arrow. It's a double arrow. Okay? So at equilibrium, the hydrogen is going to be 3 minus X. F is going to be 3 minus X. And the HF will be 3 plus 2X. Okay? Yeah, we know K. Now, the other thing I want you to pay attention to that I forgot to circle because I went to the blank page is go look at your volume. What does your volume say?
It's 1.5.
1.5 liters. So when you see that it's that, you should circle that and put a star by it so that you don't forget to account for that at the end. Otherwise, you will not get the correct answer, and it would be a shame to do all of that work, and then because you didn't divide by volume, you didn't get the right answer. So they gave us that K was 115, right?
Yes.
So K is equal to 115. So let's go ahead and just do this. So it should look like this, right? HF squared over H2 and F2. Sorry, my brackets kind of went together there. So we're going to say 115 is equal to 3 plus 2x squared over 3 minus x, 3 minus x, which is essentially what on the bottom? Squared. So what can I do to simplify my math? Square root of it. Okay? So then that would give me over here, I'm going to do a different color so you can see a little bit better. Let's go with blue. Okay? So now over here I would have 10.7 is equal to 3 plus 2x over 3 minus x. So now what do we do? Good old-fashioned, which is also called algebra, because we got some x's in there. Do some good old-fashioned algebra. Okay? So do I need to go through it, or can I just go back to the end? Okay. So then that would give us 32 I can't read my writing. 1, I think. Minus 10.7x is equal to 3 plus 2x. Surely you can go from here. So do all the math. Do the math. And x is equal to 2.29. Is that what you guys got? Goody goody, gumdrops. So now plug in x. Okay? So here's what you can do on the AP exam to save time. We know that our concentration of our two reactants are going to be equal here. So we're going to say 3 minus 2.29 divided by 1.5. Why? Yeah, so then we're going to get 0.47 molar.
So this is mole.
Yeah, because they gave it to us in moles. And then I'm running out of room. Let me do it in another color so that you can see this, just because it's, and then HF is going to be 3 plus 2 times 2.29 divided by 1.5, and you should get 5.05 molar. Make sense? Yay or nay?
Yay.
Okay. This thing does weird things. It's still on mine, and it just disappears. It's like possessed or something. It's the alien in there working it. Okay? No, that's not bad. No, the rice tables aren't bad. You do have to know how to do them. Yeah, for sure. And they're going to show up in KSP. They're going to show up in acid base. So the next one I want to do is not going to come out to nice, pretty math like that, which we like. Most of the time on the AP exam, they will come out to pretty math like this. Okay, just because the other way takes time. But that's why if you had a calculator and you want me to put the quadratic equation in there, you just enter in ABC and it gives you the answer. Okay, if you don't have your calculator with you and you want me to put that on later, let me know and I will. Okay, just don't go telling the math teachers I'm giving you the quadratic equation. I don't know about here because I haven't done it here, but my old school, they didn't care, but some get upset because they want you to actually write and you can't use it anyway on the test, right? Can you even use calculators in calculus?
Not really.
Yeah, so it won't help you.
Actually, well, a couple
Yeah.
of tests you have, so the majority
Yeah.
don't.
So you still need to know how to do the quadratic equation for your math classes, But for in here, that's not what I'm testing. I want to know if you can solve the problem. Okay? So let's look at the, oops, that's too far. Let's look at, do you have exercise 12? Where's it? It's missing from on mine for some reason. Is it really? A J is lying. Okay, so exercise 12, we've got, this time we're making the friendly acid, or the friendly one. So we're going to have H2. Can you see that green very well? Yes? No? Okay. I2 making 2HI. This is, some people, that's why some people call them ice and not rice, just because the reaction, but whichever is, I don't care. It is, I forget to do the reversible. Okay. All right, so what they gave us in the problem was that we had, first of all, this time we got a 5-liter flask. What? Okay. But they're giving us atmosphere, so do we care about the size of the flask?
No.
You are correct, we do not. So we have 0.01 atmosphere, 0.005 atmosphere, and 0.5. Okay? And so we're going to be, what did they give us? They give us K?
Yes.
And what was K?
100.
100. Okay? So, at the gaseous, I would suppose HI and R, calculate the equilibrium pressures. Why am I not seeing where KP is?
It says equilibrium constant is whatever.
I am totally not seeing it.
Second line.
Okay, there it is. It's 100. Okay, thank you. I was like not seeing that at all. Okay, so okay, for some reason on this one, I don't know why I'm seeing that I had plus X and minus over here. And I don't know why I have that. I'm thinking that I had a reason for that last year, and I don't know what it is. Because this said plus X minus 2X. Because then I have a big arrow saying it's going to lie this way. Calculate the equilibrium pressures of all the species. Huh? That's what I'm trying to remember, but this is the math, so I've got to. That's why I need to stop and read the problem. Okay, multiply and collect your terms. I did something wrong. Let's see. So obviously, because the bottom is not the same, we can't do the whole square root. Yes? Oh, 100. That was the value. So yes, I figured out what it is. So over here in my margin, which I didn't read, you calculate Q. okay? Because you have initial concentrations, and you'll calculate Q, and you'll find that Q is much greater at these concentrations than K. And so if Q is greater than K, what happens? It shifts to the left. So that's why this is going to shift this way. And so really that's the reaction that's going to happen. So now, since it's happening that way, that's why it's minus and plus. Does that make sense?
So before we do this, we have to calculate Q?
Yes. Okay. So, yes. So let's ignore this for a minute. So if I calculate Q, right, I get 0.5 squared times 0.01 times 0.005, and it comes out to 5,000, which is much greater than K. And so when Q is greater than K, which way does the reaction shift? To the left, towards the reactants. So this reaction is going to be, because this is a reversible reaction, it's going to be very strongly favored to go that direction. So that's why we did plus X, because that's actually what's going to be created, and the HI is actually going to be depleted. Sorry, I have that written over here, and that's why I was confused as what I did. This is what happens when you do this like 3 years ago. I worked this problem 3 years ago. And I was so worried about plugging in the quadratic equation in my calculator and getting those answers. So is everybody on board with what I just did?
So the 96x squared plus 3.5x, that's right?
Yes.
Okay.
Yes, because of the plus and the minus.
Yeah.
Okay? So now, obviously, that's not going to make some nice, pretty... So this is going to be our quadratic equation, which is ax squared, bx, and then the minus c in this case, since it's minus. So if I plugged that into your calculator, you'll just hit one program, and it'll ask you for A, it'll ask you for B, it'll ask you for C, and then it'll give you two roots, okay? So we're dealing with concentrations here. One of your roots is going to be negative. What do we do with that one? Ignore it, right? So after we do the quadratic equation, we'll get x is equal to 0.035. Now you can plug in those numbers. So H2, I'm going to erase this, we have room. Y'all already wrote that down, right? It's going to be 0.01 plus 0.035, which is going to be 0.045 atmosphere. And then I2, 0.005 plus 0.035 is 0.04. And then HI, 0.5 minus 2 times 0.035. So 0.43. Okay?
You don't have to use the volume in this one because it's like...
No, because we're dealing with atmosphere. But if we had been dealing with, if they had given us concentration, then we would have to divide by volume to get moles, do our rice table, and then we'd have to put it back in concentration at the end. So that's something to be mindful of.
Okay.
Okay? Yes, ma'am. When you've got if you're not giving concentrations of everything, then not necessarily. But since we had concentrations of everything, we were given KP, we kind of do need to know which way it lies. The last one, all of our moles were equal, and so it wasn't really necessary. Okay? But this one, since you've got your K value and your concentrations are vastly different, and you've got one that's a lot higher atmospheric pressure than the other one. Okay? And if you kind of look at that, does it really make sense to start out with 0.01 and 0.05 and to get 0.5 if we're going forward? It doesn't initially. So the fact that you had a lot more of the product's pressure is an indication that, hey, I might need to check and see if it's going to go the other way. And I apologize, I didn't read my margin because I have a big arrow on the top, and I knew that for some reason it shifted that way, but I forgot to look at that margin. Now let's go to LeChatlier. So there's no calculations involved in LeChatlier. Okay? Okay, so in Chem 1, we did LeChatlier. Remember, it says if a stress is applied to a system, the position of the equilibrium will shift in the direction which reduces the shift or reduces the stress. Okay, we want to keep in mind one of the things is this equation. So when we're talking about how it's going to reestablish its equilibrium, when you are answering questions on the AP exam, please do not say, because LeChatlier's principle, it's going to do this. Okay? You need to say, in order to minimize the stress, the reaction will either produce more products or produce more reactants. Okay? LeChatlier is an explanation for you to understand, but don't say because of LeChatlier. They want you to understand why it's shifting to minimize the stress. Okay? For instance, if you're looking at this and you increase the products, what's going to happen to your Kp value? It's going to get bigger. Okay? And same thing if you were to increase your reactants, the Kp is going to get smaller because of where you're putting stuff in the equation. Okay? Adding or removing reagents causes the equilibrium to shift. And this is not my example, but it's a good example. As long as you keep milking mama cow, it'll keep making milk. That's not my example. It's in the notes. I didn't come up with that example, but it is actually a good example. Huh? I didn't hear that. I'm going to ignore it. I don't know what he said. Increasing pressure. This was a big one in last year. Increasing pressure caused the equilibrium to shift to the side with the fewest number of moles of gas. The obviously opposite. If you decrease the pressure, where is it going to shift to? More moles. It's going to be opposite. It's vice versa. Okay? So most of these you just kind of have to walk through them. Adding a catalyst has no effect. Okay? Just causes the equilibrium to be reached faster, but it does not change the equilibrium position. And then, of course, we talked about this in the past. Changing the temperature, you kind of treat it as a reactant or as a product. If it's an endothermic, you're going to treat heat as a reactant, and if it's exothermic, treat it as a product. So kind of the same thing, adding product or removing product, whatever. Okay? And then they're showing you this that you can kind of work through if you want to write it that way. Always, whenever you see, sometimes they'll put the heat in the equation. Sometimes they tell you what delta H is. So if it's positive, add it to the reactant. If delta H is negative, add it to the product side. We did that in thermochem, so you should remember that. So let's just walk through a couple of scenarios, okay? So I have this equation. It doesn't have any gas on the reactant side, so only gas on the product side. It says predict the direction of the shift with response to these conditions. So if I add carbon monoxide, what's going to happen? Right, because I'm adding more of this, and it shifts away from where I added the stress, so it's going to shift this way. Okay? What if I remove the carbon or the tetra-arsenic hexoxide?
It's not in like the equation though.
Right, bingo. Those are both solids. They don't appear in the equilibrium equation. So there would be no effect, no shift. Okay? It wouldn't change anything because solids and liquids, remember, don't appear in our equilibrium expression.
And we're talking about K, right? Shifting
K, yeah. Well, because K is the equilibrium position, so we're talking about shifting that.
Okay.
So since they don't appear, it wouldn't have an effect. So that was a good job there. Yeah, I think you get a Starburst for that. Okay. And then removal of gaseous arsenic. Shift right, because I'm removing, so the equilibrium position is going to shift towards where I removed it. Okay. And I think there's quite a few questions about shifting in your packets. Okay. Here we're going to predict the shift of the equilibrium position. So I have liquid phosphorus being produced from solid phosphorus and when the volume is reduced. I was like, what are we shifting here? I didn't see the volume is reduced. Okay? So if I'm dealing with the gas and I reduce my volume, what am I essentially doing?
Increasing pressure.
Mm-hmm. So if I'm increasing pressure,
There's less moles.
yeah, good. Or in this case, it would be like increasing concentration. since we don't have moles, but if I decrease my volume for this, basically I'm going to be increasing my concentration because now I have more particles in a smaller volume. Right? Does that make sense?
Yeah.
Okay. And then what about the next one?
Where would it shift to that?
Now this time I've got 2 moles of gas, 1 mole of gas. This time everything's all gas. So when I decrease my volume, I increase my pressure, so it's going to shift to the side with fewer moles.
Where would it shift in the first one?
We said shift right.
Oh.
It would shift right, shift right. But for different reasons. And then the last one, everything is gas. I have 4 moles and 4 moles.
So,
Nothing, no shift. It wouldn't cause a shift because I have equal number of moles.
Can you talk about the first one again?
Mhm.
Why it shifts to the right? I know it has a higher.
Okay, so when you're changing volume, you have to look at 2 things. Okay, I'm increasing my pressure. Actually, volume, yeah. So, but also when you're talking about gas particles and I decrease my volume, what happens to the concentration of that gas? It increases because now you have same amount of particles, smaller volume, so you have a higher concentration because concentration is volume per, particles per volume, moles per volume. So in this case, since we're not dealing with gases on both sides, we would say, okay, well, essentially I'm increasing the pressure of chlorine. Not pressure, increasing the concentration. And when I increase the concentration, it shifts away from it. So it's going to go towards the other side.
So because you have to look at it because it's a liquid.
Yeah, and it's making a liquid. It's not making a gas. So gas is different when they're gas. But if you've got other things, you got to think about in terms of when I decrease volume, I'm basically increasing the concentration because there's more particles, same amount of particles, but less space, so it's higher. Yeah. Yes.
So when you're decreasing the volume, I guess it's pretty like it's more water.
Think of a balloon. Okay. If I have a certain amount of gas in there and I squish my balloon, okay, first of all, my pressure obviously increases, but the particles that were in there for concentration-wise, for volume, moles per volume, now I have the same amount of moles, but I have a smaller volume. So the concentration of them is higher. Does that make sense? Let's say I have five moles of gas in a balloon, and my balloon is 1 liter, and I squish my balloon down. Still have 5 moles of gas, but now I only have half a liter of volume. So if I do the math, my concentration of the particles increased. Not pressure. The pressure increases also, but that's a different side.
Because the moles is moles per liter.